What lies beyond the edge of our universe? In tonight's calm journey, we'll explore horizons of space and time with simple, gentle science. Let curiosity guide you as knowledge unfolds in a rhythm as steady as rest. Stay with us until the end. This is the Sleepy BrainDose. When you listen to this chapter, you will gently discover what scientists mean when they speak about the edge of the universe. You will learn that the universe does not have a solid wall or boundary, but rather limits defined by what we are able to observe. Along the way, you will understand how light and time set these limits, why the expansion of space matters, and what questions remain open. This beginning is a quiet invitation to explore a vast topic, step by step, in a way that remains clear and calm. That the phrase edge of the universe can sound dramatic, as if there were a cliff in space beyond which nothing exists. In reality, the situation is far more subtle. Modern cosmology shows that the universe is not structured like a room with walls or a container with sides. Instead, it is a fabric of space and time that stretches in all directions, shaped by its history and by the laws of physics. When astronomers talk about an edge, they mean the furthest distance from which light has had time to reach us since the beginning of the universe. This is often called the observable universe. The observable universe is limited by the speed of light and by the age of the cosmos. Light does not travel infinitely fast. It moves at a constant finite speed of about 300,000 kilometers per second. The universe itself has a finite age of around 13.8 billion years. That means there is only so much distance from which light could have reached Earth since the Big Bang. If something lies farther away than that distance, its light simply has not had time to arrive here yet. It remains hidden beyond our cosmic horizon, even though 13.8 billion years sounds unimaginably long. The actual size of the observable universe is much larger than 13.8 billion light years. Because space itself has been expanding since the Big Bang, galaxies that emitted their light long ago are now much farther away than they were when that light first set out. Today, the boundary of the observable universe is roughly 46 billion light years in every direction. This forms a sphere around us, centered not on Earth as a special place, but on the point in space where we happen to observe. Every observer anywhere in the cosmos would find themselves at the center of their own observable universe. Thinking about this can be grounding. Instead of picturing a hard surface at the edge of everything, it may help to imagine an expanding bubble of visibility. Within the bubble are all the galaxies, stars, and structures we can measure. Beyond it, the universe likely continues, but remains invisible to us. At least for now, this concept leads naturally to questions. If we cannot see beyond the observable universe, does that mean nothing is there? Scientists are careful here. Evidence strongly suggests that space does extend beyond what we can observe. Patterns in the cosmic microwave background radiation, the large-scale distribution of galaxies, and the uniformity of physics across billions of light years all point to the idea that the cosmos continues well past our horizon. But because we cannot measure directly, we must treat this as an informed inference, not as a certainty. The calm pace of cosmology is shaped by evidence. Astronomers use telescopes across many wavelengths of light radio, infrared, optical, ultraviolet, X-ray, to trace signals that come from the distant universe. Each signal carries information about a moment in time, since looking further away is also looking further back. This method allows us to reconstruct the history of the cosmos from its earliest hot plasma state to the galaxies we see today. By tracing this history, scientists refine their understanding of how far the observable boundary stretches. One can compare this to listening to a soft echo in a large hall. The echo tells you about the shape and size of the space, even if you cannot see its farthest walls. Similarly, the radiation and light arriving from the early universe inform us about regions beyond direct sight. This gentle metaphor reflects how cosmology uses indirect signs to sketch the unseen. Importantly, the edge we describe is not fixed. As time goes on, light from more distant regions has a chance to reach us. Our observable universe expands in terms of what we can detect. At the same time, however, the universe itself is stretching faster and faster because of dark energy. This creates a paradoxical situation. Some regions that are currently observable may drift so far away that, in the deep future, their light will never reach us again. The cosmic horizon is therefore dynamic, shaped both by the passage of time and by the expansion of space. The scale involved is vast, but the principles are simple. A finite speed of light, combined with a finite age of the universe, means we can only see so far. Expansion stretches the distances, making the boundary farther than a simple multiplication of speed and time. These ideas are fundamental to understanding any further discussion about what might lie beyond dot by approaching the subject in this way. You can notice how the edge of the universe is not a sharp line, but a gentle transition from what is visible to what is hidden. This distinction provides the foundation for deeper explorations, including the role of cosmic expansion, the nature of the background radiation, and the philosophical questions of whether beyond has meaning at all dot to continue smoothly. The next step is to understand how light acts as our main guide to these boundaries, shaping the very way we define the cosmos we live in. When people hear the phrase edge of the universe, it can easily trigger images of a physical boundary, a wall of matter, a curtain of stars, or a sudden drop into nothing. Yet modern cosmology teaches that the universe is not shaped like a container with walls. It is not enclosed, and it does not end in a literal border. Instead, what we call the edge is a concept tied to observation and measurement. It is the limit of what we can detect, not necessarily the limit of what exists. Astronomers distinguish between two related ideas: the observable universe and the entire universe. The observable universe is the portion from which light and other signals have had enough time to reach us since the Big Bang. The entire universe may be much larger, possibly infinite, but we cannot confirm its full extent, because information cannot travel faster than light. This difference is crucial. When we talk about edges, we are always speaking about edges of knowledge, not about a cosmic wall dot. To understand this better, it helps to recall what space-time itself is. In Einstein's theory of general relativity, space and time are woven together into a four-dimensional fabric. This fabric has no outer surface in the ordinary sense. The geometry of space-time can curve, stretch, and evolve, but it does not require an outside into which it expands. In fact, the question, what is outside the universe, may be as meaningless as asking, what lies north of the North Pole? The coordinates themselves end, not because of a barrier, but because the framework does not extend further. The observable edge arises because of two main constraints: the finite age of the universe and the finite speed of light. Since the cosmos is about 13.8 billion years old, light from farther than 13.8 billion light years has not had enough time to arrive. But due to the expansion of space, the actual radius of the observable sphere is about 46 billion light years. That means the farthest galaxies we can see today are not 13.8 billion light years away in present distance, but more than 3 times farther. Their light was emitted long ago, yet the space between us has stretched during the time. The light was in transit, It is important to emphasize that the observable edge is not a permanent boundary. As time passes, light from more distant regions has time to reach us, and the observable universe slowly grows. At the same time, the accelerating expansion of space means that some galaxies now visible will eventually slip beyond our horizon. In the very distant future, only our local group of galaxies may remain observable. The edge is therefore not fixed, but dynamic, changing with cosmic history. Another way to think about the edge is through the concept of the particle horizon. This is the maximum distance from which particles, such as photons, could have traveled to us since the beginning of the universe. Beyond this horizon, events are causally disconnected from us. No signal has had the opportunity to cross the intervening space. It is not that those regions do not exist. They simply remain outside our causal contact. This idea of causal separation is central to cosmology. In science, cause and effect can only be traced within regions that are in communication. When we say that a galaxy is beyond the edge, what we mean is that no information from it has yet reached us, nor ever will if the expansion prevents it. Thus, the edge is really a boundary of communication, not a wall of matter. If we imagine the universe as infinite, then the observable part is like a small bubble within an endless expanse. If the universe is finite but unbounded, like the surface of a sphere, then we still perceive only a limited portion of it. Both possibilities are consistent with our current data. Measurements of the cosmic microwave background radiation indicate that the geometry of the universe is very close to flat, which suggests either an infinite size or one so large that its curvature is undetectable within our horizon. Sometimes, people ask whether traveling fast enough could allow us to reach the edge. The answer is subtle. No matter how fast we move, we remain limited by the speed of light and by the expansion of space itself. Galaxies are not rushing through space like cars on a highway. Rather, the fabric of space between galaxies is stretching. This means that even at maximum speed, regions beyond the horizon remain unreachable. They are receding faster than light relative to us, not because they break the speed limit, but because space itself is expanding. This distinction is essential in modern cosmology. The observable edge also teaches us about the early universe. When we look toward the limits of our view, we are not only looking far away in space, but also far back in time. Light from the most distant galaxies shows them as they were billions of years ago. At the very edge, we see not galaxies at all, but the faint glow of the cosmic microwave background. This radiation comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and for light to travel freely. Beyond that time, the universe was opaque, filled with a hot plasma. Thus, our vision meets a kind of temporal horizon, a fog beyond which direct observation is impossible. This limitation does not mean our curiosity stops. Scientists use indirect methods, such as studying patterns in the background radiation or searching for subtle signals like gravitational waves, to probe conditions earlier than the microwave background. These tools allow glimpses into epochs otherwise hidden, but the principle remains the same. Our knowledge is framed by horizons, not by solid walls. At this point, it may be useful to pause and reflect. The concept of an edge in cosmology is more about what we can know than about what exists. It is a boundary of information shaped by the laws of physics. Just as one might gently notice the rhythm of a breath as it marks a cycle within the body, astronomers notice the cosmic horizon as a cycle of knowledge, marking the extent of communication between us and the wider universe. The metaphor is quiet, but it helps to place our understanding in perspective. The clarity of this idea prepares us to move deeper. To define the observable edge, we must rely on light as our messenger. In the next step, we will follow light itself, how it travels, how it reveals, and how it silently shapes the limits of our vision. When we try to understand the shape and size of the universe, light becomes our most reliable companion. It is the messenger that carries information across the vast distances of space. Every star, galaxy, and distant cloud of gas sends out radiation, and a small fraction of it eventually reaches Earth. By studying this faint stream, scientists learn not only about the objects themselves, but also about the limits of what can be observed. The very idea of an edge of the universe is defined through light. Light is part of the electromagnetic spectrum, a family of waves that includes radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each has its own wavelength and frequency, but all travel at the same universal speed in a vacuum, about 300,000 kilometers per second. This constancy was one of the great revelations of physics in the early 20th century. It means that no matter how fast an observer moves, the speed of light remains unchanged. This property sets the ultimate limit for information transfer and makes light a natural ruler for cosmic distance. When astronomers measure faraway galaxies, they rely on the fact that light takes time to travel. A galaxy 1 billion light-years away is seen not as it is now, but as it was 1 billion years ago. Looking deeper into space means looking further back into time. This time delay provides an extraordinary opportunity. By observing distant regions, we can reconstruct the universe's history. Yet it also imposes a strict limit. There are regions so far away that their light has not had time to reach us. Those regions remain invisible, hidden beyond our horizon dot. The expansion of the universe adds another layer. As light travels through space, the very space it moves across is stretching. This stretching elongates the wavelength of the light, shifting it toward the red end of the spectrum. This effect is called cosmological redshift. By measuring redshift, astronomers can determine how fast distant galaxies are receding and how far away they are. In this way, light does not only reveal position, it also encodes information about the motion and expansion of the cosmos itself. The cosmic microwave background, often abbreviated CMB, is a perfect example of how light defines boundaries. This faint glow fills the entire sky, uniform in all directions, and represents radiation released when the universe was about 380,000 years old. Before that time, photons could not travel freely, as the cosmos was a hot plasma of protons and electrons. Once atoms formed, light decoupled from matter and began its journey across the cosmos. The CMB is therefore the furthest light we can observe directly. It acts like a screen, marking the edge of the visible universe in time as much as in space dot beyond the CMB. Light cannot serve us directly, but scientists look for other messengers. Neutrinos and gravitational waves are examples of signals that could, in principle, carry information from even earlier epochs. Neutrinos interact only weakly with matter, so a cosmic neutrino background from the first seconds of the universe should still exist, though detecting it is extremely difficult. Gravitational waves, ripples in space-time itself, could also reveal traces of cosmic inflation. Both approaches extend the principle. Every boundary of knowledge is defined by the signals that can reach us dot, even within the observable universe. Light determines what is accessible. Clouds of gas absorb certain wavelengths, leaving characteristic fingerprints in the spectra of distant quasars. Dust scatters and blocks light, hiding some regions from optical telescopes. To overcome this, astronomers use multiple wavelengths. Radio telescopes peer through dust, to map cold hydrogen clouds. Infrared instruments see warm objects otherwise hidden. X-ray observatories reveal the high-energy processes around black holes. Each window adds a layer to the map of the cosmos, and together they expand the clarity of our horizon. This reliance on light can be compared, gently, to listening for a steady rhythm in a quiet environment. Just as a soft pulse marks the boundaries of silence and sound, the flow of photons marks the boundaries of the known universe. The metaphor is simple, but it highlights how dependent our understanding is on what light can carry. Without it, the cosmos would be dark in every sense, not just visually, but info-tion-light. Light also informs us about geometry. The way it bends under gravity reveals the curvature of space-time. Gravitational lensing, predicted by Einstein and observed in countless galaxies, occurs when massive objects bend the path of light from more distant sources. By studying these distortions, scientists measure the distribution of mass, including invisible dark matter. Thus, light not only shows us the distant universe, but also acts as a probe of the structures in between. Astronomers also use light to estimate the universe's age. By observing the oldest star clusters, the faint glow of distant galaxies, and the redshift of faraway objects, they can trace back cosmic expansion to a beginning. These measurements converge on the now well-accepted figure of 13.8 billion years. Light, in this way, becomes a cosmic clock. Its travel time records the unfolding of history across billions of years. The dependence on light does bring limitations. We cannot see beyond the observable universe because light has not had time to arrive. We also cannot directly witness the universe before it became transparent. Yet rather than a weakness, this limitation defines the beauty of cosmology. It frames the questions clearly. What lies beyond the reach of light? How can we infer the unseen from the seen? These questions guide the next steps in science. The practical methods of astronomy show the patience required. Observatories sit high on mountains or in space itself, far from the atmosphere's distortions, collecting photons one by one. Sun telescopes survey the entire sky, mapping billions of galaxies. Others focus on a single patch, integrating light for weeks to reveal objects otherwise invisible. Each photon is precious, a quiet messenger crossing unimaginable distances. Together, they build the picture of the cosmos that we call the observable universe. As technology improves, we learn to capture even fainter light. The James Webb Space Telescope, for instance, observes in infrared, allowing us to see galaxies form just a few 100 million years after the Big Bang. Future instruments will look even deeper, perhaps approaching the moment when the first stars ignited. Each improvement extends the edge, not by changing the cosmos, but by extending our ability to receive its light. To summarize gently, light is our definition of distance, our record of time, and our messenger of cosmic history. The concept of an edge is not a wall, but the reach of light since the beginning. Beyond it, space may stretch endlessly, but without signals, it remains unknown. Just as noticing the calm rise and fall of breath gives a sense of rhythm to the body, noticing the steady flow of photons gives a rhythm to our knowledge of the universe. From here, a natural step is to ask, how does the expansion of space itself shape these boundaries? And why does it matter that the universe is still stretching in every direction? The concept of expansion is central to modern cosmology. It is not that galaxies are flying away through empty space, like sparks from a firework. Rather, space itself is stretching, carrying galaxies along with it. This distinction is subtle but important. It explains why distant galaxies seem to recede faster than light. why the universe has no center of expansion, and why our observable horizon is defined the way it is. The idea of cosmic expansion was first discovered in the early 20th century. Astronomer Edwin Hubble observed that light from distant galaxies is redshifted, meaning its wavelengths are stretched toward the red part of the spectrum. The farther away a galaxy is, the greater the redshift. This relationship, now known as Hubble's law, revealed that the universe is not static, but expanding. The galaxies are not simply moving through space. The space between them is increasing. To picture this, scientists often use analogies, though none are perfect. One common example is a balloon being inflated, with dots on its surface representing galaxies. As the balloon grows, the dots move apart, not because they travel on the surface, but because the surface itself is stretching. Every dot sees all others moving away, just as every galaxy observes others receding. The balloon analogy is limited, since it suggests an outside, while the universe does not expand into anything. Still, it captures the idea that expansion is intrinsic to space itself. The mathematics behind this is encoded in Einstein's equations of general relativity. These equations allow space-time to curve and evolve depending on the energy and matter it contains. In 1922, Russian physicist Alexander Friedmann found solutions showing that the universe could expand or contract. Soon after, Georges Lemaître proposed that our universe began from a compact, dense state, later called the Big Bang. Hubble's observations confirmed that these theoretical solutions described reality. Expansion is not uniform in all details, but on the largest scales, it is smooth and isotropic, meaning it looks the same in every direction. Local regions, like galaxies and clusters, are bound together by gravity, resisting expansion. The solar system, for example, does not stretch as space expands. Instead, expansion dominates only at intergalactic distances, where gravity cannot hold structures together. One striking feature in expansion is that it has been accelerating for the last several billion years. Observations of distant supernovae in the 1990s showed that galaxies are not only receding, but doing so faster and faster. This discovery led to the concept of dark energy, a mysterious form of energy that permeates space and drives acceleration. Though we cannot see dark energy directly, its effects are measured in the way expansion changes over time. It now appears to make up about 70% of the universe's total energy content. The rate of expansion is described by the Hubble constant. Current measurements give values around 70 kilometers per second per megaparsec, though different methods yield slightly different numbers, leading to what scientists call the Hubble tension. This means there may be unknown physics influencing the early universe or the behavior of dark energy. The debate shows how expansion remains an active field of research, not a closed chapter. Expansion has deep consequences for our understanding of the cosmos. Because space is stretching, galaxies beyond a certain distance recede faster than light relative to us. This does not violate relativity, since the galaxies are not moving through space at that speed, but are carried apart by the expansion of space itself. Still, it means their light can never catch up to us. As a result, parts of the universe are permanently inaccessible, even in principle. This brings us to the concept of the cosmic event horizon. Just as a black hole has an event horizon beyond which no signal can escape, the accelerating universe has a horizon beyond which light emitted today will never reach us in the future. Currently, this horizon is about 16 billion light-years away. Galaxies beyond that distance are receding so quickly that their signals cannot overcome the expansion. Over time, more galaxies will slip beyond this limit, leaving fewer visible. Far in the future, observers in our galaxy may see only the faint glow of local stars, with the rest of the cosmos hidden forever. The expansion also explains why the observable universe is larger than its age in light years. Because space is stretched during the journey of light, objects that emitted photons billions of years ago are now tens of billions of light years away. Without expansion, the universe would be a smaller, simpler sphere of visibility. Instead, it is a dynamic structure shaped by the flow of time and the growth of space. That one quiet metaphor may help. Expansion is like the slow unfolding of a fabric under gentle tension. The threads do not rush outward, yet the distance between them increases. Similarly, galaxies do not surge through the void, but the cosmic fabric carries them apart. This picture is not literal, but it conveys the softness of the process. Gradual and steady expansion is also the reason why we see a cosmic microwave background. In the early universe, radiation had much shorter wavelengths. As space stretched, these wavelengths grew longer, cooling the radiation to the microwave band we measure today. Without expansion, the cosmos would still glow with blinding intensity. Instead, the stretching of space diluted and softened the primordial light into the faint background that now surrounds us. Understanding expansion also helps answer philosophical questions. If the universe is infinite, expansion simply increases the distances within it. If the universe is finite but unbounded, like the surface of a sphere, expansion changes its scale without requiring an outside. In either case, expansion tells us that the cosmos is not static. It evolves, and with it, our place and perspective. From a practical standpoint, expansion shapes astronomy at every level. The redshift of galaxies is the basic tool for mapping the large-scale structure of the universe. The growth of cosmic voids and clusters reflects how matter responds to expansion and gravity together. The formation of stars and galaxies themselves is influenced by how rapidly space stretches. Expansion is therefore not only a background fact, but an active participant in cosmic history. To bring this chapter together, the expansion of space is the quiet force that defines the universe's present and future. It explains why galaxies move apart, why horizons exist, and why the cosmos looks the way it does. Just as steady breathing sets the rhythm of rest, expansion sets the rhythm of cosmic time, unhurried and vast. With this foundation, the next step is to consider a related concept, the cosmological horizon, the subtle boundary that marks the limits of what is causally connected to us in the expanding universe. In cosmology, the word horizon does not describe a line where the sky meets the sea, but rather a boundary in knowledge. It is the limit of what can be observed or influenced in an expanding universe. Just as an earthly horizon hides what lies beyond, the cosmological horizon hides regions of space that light or any signal cannot reach us from. Unlike the edge of a map, this horizon is not fixed in space. It changes with time and depends on the physics of expansion. There are several horizons in cosmology, each with a precise meaning. The particle horizon marks the maximum distance from which light has reached us since the beginning of the universe. It defines the observable universe, a sphere of about 46 billion light years in radius. Beyond this limit, no particle, no photon, no signal has had enough time to arrive here. The particle horizon is essentially the historical boundary of what we can see. The event horizon, by contrast, points to the future. It defines the maximum distance from which light emitted today will ever be able to reach us, even if we wait forever. Because the universe is accelerating in its expansion, driven by dark energy, there are regions that are already receding so quickly that their light will never catch up. At present, this cosmic event horizon lies at roughly 16 billion light-years. Any galaxy beyond that distance is permanently unreachable. Even if it emits light now, that light will not overcome the expansion to reach our telescopes. A third concept, the apparent horizon, is used in general relativity to describe the boundary between regions moving toward and away from us at the speed of light. It provides another way of defining the causal structure of spacetime. These distinctions show that the universe has multiple horizons, each tied to a different aspect of time and causality. Understanding horizons requires returning to the relationship between light and expansion. Light travels at a constant speed, but space itself stretches. The further away a galaxy is, the faster it appears to recede. At a certain distance, called the Hubble radius, recession speed equals the speed of light. Yet even galaxies beyond this distance can sometimes be observed because their light was emitted long ago, when they were closer, and has been traveling ever since. The difference between what we can see now and what will remain visible in the future is the essence of cosmological horizons. The particle horizon defines the limit of our past communication. The event horizon defines the limit of our future communication. Together, they map out the possible exchange of information in the universe. Within the horizon, galaxies can interact, at least in principle. Beyond it, they are forever separate, part of the same cosmos, but cut off by expansion. This separation does not mean those regions do not exist. It simply means they are causally disconnected from us. In physics, causality is the chain of cause and effect. Horizons mark where that chain ends, not because of a law, but because signals cannot cross fast enough to connect both sides. It is a boundary in communication, not in substance. To visualize this, cosmologists often use space-time diagrams. In these diagrams, time is represented on one axis and distance on another. Light always travels at the same angle, forming cones of causality. The region inside the cone is what can influence an observer. The horizon appears as the edge of this cone, separating reachable events from unreachable ones. Though abstract, these diagrams capture the quiet precision of how horizons work. The existence of a cosmic event horizon carries profound implications for the long-term future. As time passes, more galaxies will cross beyond it, slipping away into unreachability. The night sky billions of years from now will gradually grow emptier. Distant galaxies will fade, their light stretched into undetectable wavelengths. Eventually, only the local group our Milky Way and its neighbors will remain bound together. For future observers, the wider universe will be invisible, hidden behind a horizon they cannot cross. This raises philosophical questions. Are those distant regions part of our universe if we can never interact with them? In physics, the answer is yes. They remain part of the same continuous space-time, governed by the same laws of nature. But from a practical standpoint, they are forever beyond reach. The horizon divides not existence, but accessibility. Horizons also appear in other contexts. A black hole, for instance, has an event horizon from which nothing can escape. The cosmic event horizon is similar in principle, though far less extreme. Both represent limits of communication set by the structure of space-time itself. These parallels highlight the universality of horizons in relativity. They are not accidents, but natural consequences of finite speed and expanding geometry. It is worth noting that horizons can shift depending on the cosmic model. If dark energy changes its behavior, the event horizon may move. If the universe were to stop accelerating, the horizon could disappear, allowing light from distant galaxies eventually to reach us. These possibilities remind us that horizons are tied to physics, not absolutes. They describe the current conditions of expansion and energy, and they evolve as the universe evolves. One gentle metaphor may help to close this chapter. Horizons are like the slow dimming of sound in a wide landscape. As the source moves away, the sound waves stretch until they fade beyond hearing. Nothing sudden occurs, no wall, no cutoff, only a gradual slipping into silence. In the same way, cosmic horizons mark the soft transition between regions. We can reach and regions that quietly recede beyond connection. With this understanding, we see that the cosmological horizon is not a boundary of existence, but of interaction. It is shaped by the expansion of space, by the finite speed of light, and by the presence of dark energy. It tells us not where the universe ends, but where our communication with it ends. This reflection leads naturally to the next step, the study of the cosmic microwave background, the ancient radiation that serves as the most distant light we can observe, marking a special horizon in time as well as in space. Among all the signals that reach us from space, one stands out as both the oldest and the most important. It is not the light of stars or galaxies, nor the bursts of energy from quasars or supernova. Instead, it is a faint, uniform glow that fills the entire sky, coming equally from every direction. This glow is called the cosmic microwave background, or CMB for short. It represents the oldest light we can observe, a direct remnant of the early universe, preserved for nearly 14 billion years. The story of the CMB begins shortly after the Big Bang. In the first few 100,000 years, the universe was hot and dense, filled with a plasma of protons, electrons, and photons. In that environment, light could not travel freely. Photons were constantly scattered by charged particles, much like beams of light are scattered in thick fog. Space was opaque, preventing radiation from moving across long distances. As the universe expanded, it cooled. About 380,000 years after the Big Bang, temperatures dropped enough for protons and electrons to combine into neutral atoms. This process, called recombination, allowed photons to travel without constant scattering. The universe suddenly became transparent, and light was released in all directions. Those photons have been traveling ever since, stretched by cosmic expansion into microwaves. What we see today as the CMB is that ancient light, still carrying the imprint of the conditions from which it came. The CMB was discovered by accident in 1965 by Arno Penzias and Robert Wilson. They were working with a radio antenna and found a persistent noise they could not explain. After ruling out equipment faults and even cleaning away nesting pigeons, they realized the noise was not local at all. It came from the sky itself, equally strong in every direction. At the same time, theoretical physicists had predicted such a background as a consequence of the Big Bang. The discovery provided decisive evidence that the universe began in a hot, dense state. At first glance, the CMB appears astonishingly uniform. Its temperature is about 2.7 kelvins, only a few degrees above absolute zero, and it does not vary significantly across the sky. Yet with sensitive instruments, scientists have found tiny fluctuations, differences of only 1 part in 100,000. These small irregularities are crucial. They record the density variations present in the early universe, seeds that later grew into galaxies and clusters. Without them, matter would have remained evenly spread, and cosmic structures would never have formed. Satellites such as COBE in 1989, WMAP in 2001, and Planck in 2009 mapped the CMB in increasing detail. COBE first detected the small anisotropies. WMAP refined the measurements, providing precise values for the age, composition, and geometry of the universe. Planck offered the sharpest map yet, showing how matter was distributed just after recombination. These missions transformed cosmology from broad theory into precision science. The CMB not only confirms the Big Bang, but also constrains the universe's geometry. The size of the fluctuations depends on the curvature of space. Observations show that the geometry is remarkably flat, with only tiny deviations allowed. This means that on cosmic scales, parallel lines remain parallel, and the universe does not curve strongly inward or outward. Flatness suggests either an infinite universe, or one so large that curvature cannot be detected within our horizon. The polarization of the CMB adds further insight. Light waves can vibrate in different orientations, and the scattering processes in the early universe left a faint pattern in this polarization. Measuring it helps reveal the motion of matter and even the possibility of gravitational waves from inflation, the extremely rapid expansion thought to have occurred in the first fraction of a second. Although direct detection of primordial gravitational waves remains elusive, the CMB is one of the best tools to search for them. Another remarkable property of the CMB is its near-perfect black body spectrum. A black body is an ideal emitter that radiates according to its temperature. The CMB fits this curve almost exactly, with a temperature of 2.725 K. This precision rules out many alternative cosmological models. It shows that the early universe was in thermal equilibrium, a dense soup where matter and radiation were tightly coupled. Because the CMB is so faint and uniform, it is easy to forget its significance. Yet it is our most direct window into the early cosmos. Observing it is like seeing the first visible light after a long night. One could say gently that it is the universe's first clear breath, captured and preserved across time. That breath still reaches us, stretched into microwaves, carrying messages from a time long before stars existed. The CMB also helps determine the composition of the universe. By comparing the observed fluctuations with theoretical models, scientists conclude that ordinary matter makes up about 5% of the total. Dark matter accounts for around 25%, and dark energy for about 70%. These proportions shape cosmic evolution, influencing how galaxies form and how expansion changes. Without the CMB, we would not have such precise knowledge of these unseen components. Future missions aim to study the CMB even more closely. Ground-based observatories in Antarctica and Chile, along with planned satellites, will measure polarization with greater sensitivity. Their goal is to detect the faint signatures of inflation, testing theories about the very beginning of the universe. Each step extends our view further back, closer to the moment when space and time themselves emerged. It is important to emphasize that the CMB is not the edge of the universe in space, but in time. It marks the earliest moment from which light could travel to us. Beyond it lies an era we cannot see directly, though we can infer its conditions through other means. In this sense, the CMB is our horizon of visibility, a screen that both reveals and conceals. Bringing this together, the cosmic microwave background is the fossil light of the universe, released when matter and radiation first decoupled. It confirms the Big Bang, maps the seeds of structure, reveals the universe's geometry, and points toward mysteries yet to be solved. Just as a quiet rhythm can anchor the sense of calm in a moment, the steady glow of the CMB anchors cosmology, grounding our knowledge in a signal that has traveled unbroken for nearly 14 billion years. From this foundation, we can move outward again, turning from the earliest light to the large-scale structures it seeded, the cosmic web of galaxies and clusters, that form the visible architecture of the universe. When we lift our eyes to the night sky, we see a few thousand stars. With telescopes, that number expands to millions of galaxies. But even these galaxies are not scattered randomly. On the very largest scales, the universe has a structure, a pattern shaped by gravity, expansion, and the initial fluctuations left over from the early cosmos. This structure is sometimes called the cosmic web, a network of filaments, clusters, and vast empty regions that together form the visible architecture of the universe. That the seeds of this structure were laid in the early universe. Tiny variations in density, recorded in the cosmic microwave background, gradually grew under the influence of gravity. Regions slightly denser than average attracted more matter, growing into larger clumps. Over billions of years, these clumps became galaxies and clusters, while underdense regions expanded into cosmic voids. In this way, the entire visible universe arose from minute differences measured in parts per 100,000 out on scales of hundreds of millions of light years. Galaxies arrange themselves into filaments long, thread-like chains that can stretch for hundreds of millions of light years. Between the filaments are voids, regions where relatively few galaxies exist. Together, the filaments and voids form a web-like pattern, giving the cosmos a strikingly interconnected appearance. Computer simulations, based on the physics of dark matter and expansion, reproduce this pattern in detail, confirming that gravity acting on invisible dark matter is the main driver of cosmic structure. Clusters of galaxies mark the nodes of this web. They are the densest regions, containing hundreds or thousands of galaxies bound by gravity. Between clusters lie superclusters, vast associations spanning hundreds of millions of light years. The Laniakea supercluster, which includes our Milky Way, is about 500 million light years across and contains roughly 100,000 galaxies. Within it, our local group of galaxies is a tiny island in a vast ocean of structure. The scale of these structures can be difficult to grasp. A galaxy is already immense, containing billions of stars. Yet galaxies themselves are mere points when placed into the context of filaments and superclusters. The voids between them can be hundreds of millions of light years wide. From one edge of the largest known structures to the other, distances exceed 1 billion light years. These numbers emphasize the layered nature of the universe, with complexity building from stars to galaxies, galaxies to clusters, clusters to superclusters. And beyond dot observations of the large-scale structure come from deep surveys of the sky. Projects such as the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, revealing the cosmic web in remarkable detail. New instruments like the Dark Energy Spectroscopic Instrument continue this work, measuring redshifts for tens of millions of galaxies to trace the three-dimensional distribution of matter. Each survey extends our vision, showing how the web stretches across space and evolves with time. The structures we see today are not static. Gravity continues to pull galaxies together, while expansion stretches the space between larger regions. In billions of years, clusters may merge into even larger associations, while voids may grow emptier. Yet the overall pattern, the web of filaments and clusters, remains a defining feature of cosmic architecture. It is the bridge between the tiny fluctuations of the early universe and the galaxies we see around us now. Dark matter plays a central role in shaping these structures. Although it does not emit light, it exerts gravity, pulling ordinary matter into its potential wells. Simulations that include dark matter reproduce the observed web precisely, while those without it fail to form the correct structures. This is one of the strongest pieces of evidence that dark matter exists, even though its nature remains unknown. Roughly 5 times more abundant than normal matter, it sets the framework upon which galaxies form. Superclusters are sometimes grouped into even larger features called walls or complexes. One example is the Great Wall, a filamentary structure of galaxies over 500 million light-years long. More recently, astronomers discovered the Boss Great Wall, even larger, spanning about 1 billion light-years. These discoveries challenge our sense of scale, showing that the universe contains coherent structures at nearly unimaginable sizes. Still, on scales above a few billion light-years, the distribution becomes uniform, in agreement with the cosmological principle that the universe is homogeneous and isotropic when viewed. At the largest scales, cosmic voids are equally fascinating. Though they are called empty, they do contain some galaxies, often faint and isolated. The voids occupy most of the universe's volume, making the cosmic web more emptiness than substance. These vast regions remind us that the universe is not only about what is present, but also about what is absent. The balance between voids and filaments defines the geometry of cosmic structure. A gentle metaphor may help. The cosmic web resembles a faint lace spread across an immense fabric. The threads are the filaments of galaxies. The holes are the voids. The pattern is delicate yet vast, simple in outline but rich in detail. This image, while not literal, conveys the quiet complexity of cosmic architecture. The study of large-scale structure, also connects directly to dark energy. The way galaxies cluster, the growth of voids, and the stretching of filaments all reflect the rate of cosmic expansion. By comparing observations to models, scientists measure how dark energy influences the growth of structure. In this way, the cosmic web is not only a map of the present universe, but also a tool for probing its underlying physics. On human timescales, these structures seem eternal. Galaxies will continue orbiting within clusters for billions of years. Superclusters will remain vast landmarks of space. Yet, on the longest timescales, expansion will eventually pull them apart, leaving islands of matter drifting in an ever emptier cosmos. The cosmic web is both a record of the past and a preview of the distant future. To summarize gently, the largest structures in the universe are not random scatterings, but a vast, interconnected web, born from tiny fluctuations in the early universe, shaped by dark matter and gravity, stretched by cosmic expansion. The web defines the architecture of the cosmos. Just as a calm rhythm can outline the shape of a quiet moment, the cosmic web outlines the shape of the universe itself. From this perspective, it is natural to ask what lies beyond these visible structures. Does the universe simply continue with the same pattern, or is there something fundamentally different beyond our horizon? That reflection leads into the question of what beyond might mean in cosmology. When we speak of beyond the universe, the words sound simple, but in cosmology, they carry layers of meaning. What lies outside the observable universe is not necessarily outside the universe itself. Instead, it refers to regions we cannot see because light from them has not yet reached us. Distinguishing between what is unobservable and what does not exist is the key to understanding this topic. The observable universe, as we have seen, is a sphere about 46 billion light-years in radius. It is bounded not by matter or walls, but by the time light has had to travel since the Big Bang. Beyond that sphere, space almost certainly continues. The physics we measure, laws of gravity, properties of matter, distribution of galaxies, suggests no sudden end at the edge. Instead, the structures we observe appear consistent and continuous. The safest assumption is that more of the same exists beyond our horizon, whether or not we can verify it directly. This assumption is supported by the cosmological principle, the idea that the universe is homogeneous and isotropic at the largest scales. Homogeneous means it has the same average properties everywhere. Isotropic means it looks the same in every direction. Observations of the cosmic microwave background and galaxy surveys confirm this principle within our horizon. If the universe is indeed uniform on the largest scales, then it should extend in a similar way beyond what we can see. Still, there are possibilities that challenge this view. Some theories of cosmology allow for variations beyond our observable patch. Inflation, a rapid expansion thought to have occurred in the first fraction of a second after the Big Bang, could have created regions with different properties. In some models, inflation continues eternally in other parts of space, spawning countless pocket universes with varying constants of nature. This idea belongs to the family of multiverse hypothesis, which we will explore later. But even without invoking multiple universes, inflation suggests that what lies beyond our horizon is far larger than what we can observe. The geometry of the universe also matters. If the cosmos is perfectly flat and infinite, then it extends without end. Our observable patch would be only one part of an unbounded whole. If the universe is curved, but very large, it might be finite yet unbounded, like the surface of a sphere. In that case, traveling far enough in one direction could, in principle, bring you back to your starting point. Observations so far show that space is extremely close to flat, which points toward infinite extension, or at least a size so vast that we cannot detect its curvature. Another way to think about beyond is in terms of causality. Regions outside our observable universe are causally disconnected from us. They cannot send signals to us, and we cannot send signals to them. Yet they are part of the same cosmic fabric. They share the same origin in the Big Bang, the same expansion of space, and likely the same physical laws. In this sense, beyond does not mean separate or alien, but simply inaccessible. The limits of observation also encourage humility. We cannot test directly what exists beyond our horizon. We can only infer it from the consistency of what we see within. This is why cosmology often blends physics with philosophy. Scientists must distinguish between what is measured, what is inferred, and what remains speculation. Still, the inferences are strong. There is no evidence of a boundary, and much evidence of continuity. One gentle metaphor may help frame this idea. Imagine standing in a vast, foggy plain. You can see only a certain distance around you, and the horizon is set by how far the mist allows. Beyond that, the plain almost certainly continues, though you cannot see it. Nothing suggests that the ground stops where visibility ends. In the same way, the cosmic horizon marks only the limit of our sight, not of space itself. The question of what lies beyond also touches on the possibility of different physical laws. Some speculative theories suggest that constants such as the strength of gravity or the charge of the electron could vary in other regions. Evidence for such variation is lacking. All observations within our horizon show remarkable uniformity. But if inflation created many regions with different conditions, then beyond our horizon, there could exist places where the laws of physics take slightly different forms. This remains an open question, intriguing but uncertain. Cosmic topology adds another layer. Even if the universe is infinite, it could have a complex shape, looping back on itself in subtle ways. Mathematicians describe such shapes as manifolds, higher dimensional surfaces with unusual properties. Observations of the CMB look for repeating patterns that could indicate such topologies. So far, no convincing evidence has been found, but the possibility remains. If true, Beyond could eventually lead back to within, just as traveling around Earth eventually brings you home. Beyond also has a temporal meaning. Looking past the CMB in time, not in space, we reach an era before light could travel freely. In that hidden epoch lie processes such as inflation, baryogenesis, the creation of matter over antimatter, and the first nuclear reactions. These events shaped everything we see now, but remain concealed behind the fog of the early plasma. Probing that beyond in time is one of the central goals of modern cosmology, pursued through gravitational waves, neutrino backgrounds, and theoretical models. Ultimately, the word beyond reminds us of the limits of science. Cosmology is rooted in observation, and observations stop at the horizon. What lies past it remains invisible, perhaps forever. Yet invisibility does not mean absence. The patterns we see strongly suggest continuation. The large-scale structure, the uniformity of background radiation, and the laws of physics all point outward, hinting that the cosmos extends far beyond what we can measure. To summarize, what lies beyond the observable universe is most likely more of the same galaxies, clusters, filaments, and voids stretching endlessly. Theoretical possibilities include different regions shaped by inflation or unusual topologies that loop space back on itself. But the edge of observation is not the edge of existence. Just as calm breathing extends quietly beyond awareness, the universe likely extends quietly beyond sight, vast and continuous. From here, it is natural to explore some of the most ambitious ideas about what beyond could mean, not just more of the same, but entirely new domains of reality. That leads into the discussion of multiverse theories and the bold attempts of physics to imagine other universes alongside our own. The universe we see may feel vast enough on its own. It contains hundreds of billions of galaxies, each with billions of stars, spread across distances measured in tens of billions of light years. Yet modern physics entertains the possibility that what we call the universe might be only one part of a larger reality. This broader concept is known as the multiverse. It suggests that beyond our observable horizon, or even beyond our universe itself, there could exist other regions of space-time, perhaps with different properties or even different physical laws. The multiverse idea does not arise from imagination alone. It emerges naturally from several well-developed theories in cosmology and physics. One of the strongest roots is cosmic inflation. Inflation is the theory that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially. This rapid growth smoothed out irregularities, explaining why the cosmos appears so uniform on large scales. But in many models, inflation does not stop everywhere at once. Instead, it ends in some regions while continuing in others. Each region where inflation stops becomes a bubble universe, while inflation carries on outside. The result is an ever-growing collection of universes, like bubbles in an infinite froth. This scenario is called eternal inflation, and it provides one version of the multiverse. Another source comes from quantum mechanics. In the standard interpretation, quantum events are probabilistic. A particle may have several possible outcomes, but only one is realized when measured. Yet the many worlds interpretation of quantum mechanics suggests that all possible outcomes occur, each in a separate branch of reality. Every time a quantum event happens, the universe splits into parallel versions. From this view, there could be an unimaginably large number of parallel universes, each representing a different history. A third path arises from string theory, a leading candidate for unifying physics. String theory requires extra dimensions beyond the familiar three of space and one of time. Depending on how these dimensions are compactified rolled up into tiny shapes, different universes could emerge with different fundamental constants. String theory predicts an enormous landscape of possible universes, perhaps 10,500 in number. If inflation populates this landscape, then each pocket universe could realize a different set of physical laws. These scenarios are highly speculative, yet they are grounded in mathematical models that aim to explain known observations. The multiverse hypothesis is not confirmed science, but it is taken seriously because it arises naturally when established theories are extended to their limits, that the implications of a multiverse are profound. If other universes exist with different physical constants, then our own might not be unique. The fact that our universe has conditions suitable for life could be explained by a principle of anthropic selection. In a vast multiverse with countless possibilities, observers will naturally find themselves in regions where the constants allow complexity in life. This idea is controversial because it explains features of our universe by appealing to unobservable others. Yet it provides one way to address the question of why the universe seems fine-tuned for existence. Evidence for a multiverse is difficult to obtain. By definition, other universes are outside our observable horizon. However, researchers search for indirect signs. For example, collisions between bubble universes during inflation might leave imprints in the cosmic microwave background. So far, no such signals have been confirmed. Another approach is to examine whether the constants of nature are as they must be for life. If they appear improbably tuned, that might support the multiverse idea, though alternative explanations may also exist. Philosophers of science debate whether the multiverse is testable. Some argue that it belongs to metaphysics rather than physics, since other universes may never be observed. Others point out that if a theory like inflation, already supported by evidence, predicts a multiverse, then we should take the predictions seriously. In this view, rejecting the multiverse would mean arbitrarily limiting a theory that otherwise works. Gentle metaphor may place this in perspective. Imagine standing at the shore of a calm sea. You see only the waves close to you, yet it is natural to suppose the sea extends far beyond sight. The multiverse, if it exists, would be like that sea. Our universe is one visible wave, with countless others rolling on beyond our view dot. It is important, however, to distinguish levels of speculation. The observable universe is well measured. Inflation has strong, though indirect, evidence. A multiverse remains a possibility, not a certainty. Keeping this distinction clear preserves the balance between open curiosity and cautious science. Still, the idea has value even if never confirmed. It stretches our thinking about what reality could be. It challenges the notion of uniqueness, reminding us that our cosmos might be part of something larger. It offers explanations for otherwise puzzling facts, such as the apparent fine-tuning of constants. And it connects cosmology with fundamental physics in new ways, linking the largest scales of the universe with the smallest scales of quantum mechanics and string theory. In summary, the multiverse hypothesis is the suggestion that our universe may be only one of many. It arises from eternal inflation, from interpretations of quantum mechanics, and from the landscape of string theory. While evidence is lacking, the idea remains a serious topic of study because it flows naturally from theories already under investigation. Just as calm breathing suggests continuity beyond immediate awareness, the multiverse suggests continuity beyond our visible cosmos. From here, we turn back to our own universe's geometry, asking whether it is open, closed, or flat, and what these shapes imply for the meaning of cosmic edges. When we talk about the geometry of the universe, we are not speaking about shapes like circles or triangles drawn on paper. Instead, we mean the overall curvature and structure of space-time itself. Just as the surface of Earth can be flat in one place, yet curved when viewed as a whole, the universe too has a global geometry. Understanding this geometry helps us know whether space extends infinitely, whether it eventually closes in on itself, or whether it is balanced on the knife edge of flatness. The foundations for this discussion lie in Einstein's general theory of relativity. According to Einstein, mass and energy curve spacetime, and the geometry of that curvature determines how matter moves. On small scales, this explains how planets orbit stars and how light bends around galaxies. On the largest scales, it tells us how the entire universe evolves. The solutions to Einstein's equations, first studied by Alexander Friedmann in the 1920s, describe different possible cosmic geometries. There are three main types. A closed universe has positive curvature, like the surface of a sphere. In such a universe, if you traveled in a straight line long enough, you could eventually return to your starting point. Space is finite but unbounded, just as Earth's surface is finite but has no edge. A flat universe has zero curvature, like a perfect plane. It can extend infinitely, and parallel lines remain parallel forever. An open universe has negative curvature, like a saddle, spreading out without bound and causing parallel lines to diverge. For decades, scientists debated which geometry matched reality. Observations of the cosmic microwave background provided the most precise answer. By measuring the sizes of the temperature fluctuations imprinted on the sky, cosmologists could determine the curvature. If the universe were closed, the fluctuations would appear larger. If open, smaller. Measurements from satellites such as WMP and Planck showed that the fluctuations are just the right size for a flat geometry. Within experimental error, the universe is flat to within a fraction of a percent. Flatness does not mean the universe is simple. A flat cosmos can still be infinite in extent, or it can be extremely large but finite, depending on its topology. What flatness does tell us is that the overall density of matter and energy is very close to a critical value. If density were greater, the universe would curve inward. If lower, it would curve outward. The remarkable closeness to flatness is one of the motivations for the theory of cosmic inflation, which naturally drives the universe toward flatness regardless of its initial conditions. The geometry of the universe is not just an abstract property. It has consequences for its fate. In a closed universe, expansion might eventually reverse, leading to a big crunch. In an open universe, expansion would continue forever, thinning matter to nothing. In a flat universe with dark energy, expansion also continues forever, but at an accelerating rate. Observations of supernova and the cosmic microwave background suggest that our universe is flat and dominated by dark energy, leading to endless expansion, not beyond curvature. Geometry also concerns the topology of space. Even if the universe is flat, it might have a complex global shape. For example, space could wrap around itself like a three-dimensional torus. In such a universe, traveling far enough in one direction could eventually bring you back to your starting point, even without curvature. Scientists search for signs of such topologies by looking for repeated patterns in the cosmic microwave background. So far, no convincing evidence has been found, but the possibility remains open. Understanding geometry also involves the balance of energy components. Ordinary matter, dark matter, and dark energy each contribute to the total density. Their combined effect determines curvature. Current measurements give about 5% ordinary matter, 25% dark matter, and 70% dark energy adding up to nearly the critical density. This remarkable balance is another reason cosmologists believe inflation played a role in shaping the early universe. One gentle metaphor may help. Imagine a sheet stretched evenly in all directions. If it is perfectly balanced, it remains flat. Add too much weight in one place, and it curves inward. Pull it tight at the edges, and it curves outward. The universe, too, balances matter and energy in a way that keeps it flat. Though not a literal picture, it captures the quiet precision of cosmic geometry. The pursuit of geometry connects observations across many fields. Astronomers use galaxy surveys to measure large-scale structure, gravitational lensing to map dark matter, and distant supernova to trace expansion. All these data converge on the same conclusion. Our universe is flat, or so close to flat that any deviation is beyond current detection. Yet questions remain. Why is the universe flat to such high precision? Why do the components of matter and energy balance so closely at this moment in cosmic history? These questions are at the frontier of cosmology, pointing to new physics that may lie beyond our current understanding. To bring this chapter together, the geometry of the universe is the shape of space-time itself. Observations show it is flat on the largest scales, with density at the critical value and expansion driven by dark energy. The geometry determines not only the universe's shape, but also its fate. Just as a calm rhythm can define the structure of a moment, geometry defines the structure of the cosmos. From here, it is natural to turn from space to time, asking what the concept of beyond means not only in distance, but in the direction of the past. What lies before the universe we know began? When we ask what lies beyond the edge of the universe, we often think in terms of space. Yet there is another dimension to consider: time. Just as our horizon in space is limited by the distance light has traveled, our horizon in time is limited by how far back we can look. Time, too, has a boundary. It is marked by the beginning of the universe, as we know it, what we call the Big Bang. The Big Bang is not an explosion in space, but the rapid expansion of space-time itself from a hot, dense state. Extrapolating backward through equations of general relativity, we find that the universe becomes denser and hotter as we move closer to the beginning. Eventually, the equations suggest a singularity, a point where density and temperature become infinite and the laws of physics break down. This mathematical singularity is what we call the boundary of time. However, most scientists do not believe the singularity is a literal point that existed in reality. Instead, it signals the limits of our current theories. General relativity describes space-time very well, but it does not incorporate quantum mechanics, which governs the very small. At the extreme conditions near the beginning, both theories must be combined into a theory of quantum gravity, a framework that remains incomplete. Until such a theory exists, the exact nature of the beginning of time remains unknown. Different hypotheses attempt to describe what might lie before the Big Bang. One idea is that time itself began with the Big Bang. In this view, asking what happened before is like asking what lies north of the North Pole. Time has no meaning beyond that point. And the Big Bang is the true beginning of temporal existence. This is the simplest interpretation, consistent with relativity, though it leaves open the deeper question of why the universe began at all. Another possibility is that the Big Bang was not the absolute beginning, but rather a transition. In some models, the universe undergoes cycles of expansion and contraction, known as cosmological bounces. In this scenario, our Big Bang was preceded by a collapse, and before that, another expansion in an eternal rhythm. Though attractive in concept, such models face challenges in explaining why entropy, the measure of disorder, increases from cycle to cycle. Third approach comes from the theory of inflation. Some inflationary models suggest that our observable universe was born from a small patch of space that underwent rapid expansion. If inflation is eternal, other patches may have inflated before and after ours, creating a vast ensemble. In this case, time does not begin with our Big Bang, but stretches further back, with each universe marking a new phase. This links naturally to the idea of the multiverse discussed earlier. Quantum cosmology offers additional possibilities. In the 1980s, James Hartle and Stephen Hawking proposed the no-boundary proposal, in which the universe is finite, but without a sharp beginning. In their model, time near the Big Bang becomes imaginary, in a mathematical sense, smoothing out the singularity. The universe has no boundary in time, just as the surface of a sphere has no edge in space. From this perspective, the universe simply is, without requiring a first instant. Other ideas include scenarios where the universe emerges from a quantum fluctuation in a larger background, or where time itself is emergent, arising from more fundamental physical processes. These remain speculative, but they show how actively scientists are exploring the boundary of time. Observationally, we are limited. The cosmic microwave background gives us a view back to 380,000 years after the Big Bang. Indirectly, we can probe earlier epochs through nuclear abundances, gravitational waves, or high-energy physics. But the first tiny fraction of a second where inflation, quantum gravity, and possible bounces might occur remains hidden. This is the horizon of time, a veil science has not yet pierced. One gentle metaphor may help to frame this. Consider the quiet rhythm of a clock. Its ticking measures intervals, but the clock itself must have been set in motion. In the same way, time as we know, it has intervals we can measure, but the setting in motion, the very beginning, remains outside our grasp. The boundary of time also influences the fate of the universe. If time had a beginning, will it also have an end? Current evidence suggests not, at least not in the near future. With dark energy driving accelerated expansion, time may continue indefinitely, stretching forward without bound. In contrast, in some models of a closed universe, expansion could halt and reverse, leading to a final collapse and perhaps another bounce. Whether time is finite or infinite remains an open question. Philosophical reflections naturally arise. If time began, what caused it to begin? If time is eternal, what does before even mean? These are not only scientific questions, but also conceptual ones, stretching the limits of human understanding. Science can describe how time behaves within the universe, but why it exists at all may be a question of a different kind. In summary, the boundary of time is as real as the boundary of space. Our knowledge reaches back to the first fractions of a second after the Big Bang, but beyond that, theories diverge. Possibilities include time beginning at the Big Bang, cycles of bounces, eternal inflation, or a no-boundary condition. The true nature of the beginning remains one of the deepest mysteries of cosmology. Just as a calm rhythm gives structure to a moment, the flow of time gives structure to the universe, but its ultimate origin remains hidden. From here, we can turn to another boundary, not in time, but in composition. The mysterious influences of dark matter and dark energy, which shape the cosmos yet remain unseen. As we explore the boundaries of the universe, we encounter two of the greatest mysteries in modern science: dark matter and dark energy. Together, they make up about 95% of the cosmos, yet both remain invisible and undetected by ordinary means. They are not called dark because they are sinister, but because they do not emit or absorb light. We know of their presence only through their gravitational and cosmological effects. Understanding them is essential to understanding the structure and fate of the universe. Let us begin with dark matter. Ordinary matter, the atoms that form stars, planets, and people, accounts for only about 5% of the total energy density of the cosmos. When astronomers measured the motions of galaxies, they found that visible matter alone could not explain the observed speeds. In the 1930s, Fritz Zwicky studied the Coma cluster of galaxies and noticed that galaxies were moving too fast to be held together by the gravity of visible stars alone. He proposed the existence of unseen missing mass. Later, in the 1970s, Vera Rubin measured the rotation curves of galaxies and confirmed that stars at the edges orbit too quickly. Something unseen must provide additional gravitational pull. That something is what we call dark matter. Dark matter does not interact with light, which makes it invisible to telescopes. Its presence is inferred through gravity. Gravitational lensing, where light from distant galaxies is bent by mass along the way, shows the distribution of dark matter. Computer simulations of cosmic structure, including dark matter, reproduce the observed cosmic web. Without dark matter, galaxies would not have formed as they did. Its gravitational scaffolding provided the framework for ordinary matter to collapse and form stars. What is dark matter made of? Several possibilities exist. One class of candidates is WIMPs, or weakly interacting massive particles. These hypothetical particles would have mass and interact via gravity and the weak nuclear force, but not with light. Another possibility is axions, very light particles predicted by certain extensions of particle physics. Some theories propose sterile neutrinos, or even more exotic particles. Despite decades of experiments, no direct detection has yet been made. Underground detectors, particle accelerators, and astrophysical searches continue to probe its nature. Although mysterious, dark matter behaves consistently. It interacts gravitationally, it clusters on large scales, and it explains observations from galaxy rotation to gravitational lensing. Its mystery lies not in doubt of its existence, but in the fact that we do not yet know its composition. If dark matter shapes structure, dark energy shapes destiny. Discovered in the late 1990s, dark energy is the name given to the force driving the accelerated expansion of the universe. Observations of distant Type Ia supernova showed that galaxies are receding faster than expected. Instead of slowing under gravity, the expansion is speeding up. The simplest explanation is a uniform energy filling space with negative pressure that pushes the cosmos apart. Dark energy accounts for about 70% of the total energy density. Its exact nature is unknown. The simplest model treats it as a cosmological constant, first introduced by Einstein in 1917. In this view, empty space itself has energy, which remains constant as the universe expands. This constant energy density drives acceleration. More complex models propose a dynamic field, sometimes called quintessence, whose strength changes with time. Others suggest modifications to gravity itself. The effects of dark energy are subtle yet profound. It determines the fate of the universe. In a cosmos without dark energy, expansion might slow and possibly reverse. With dark energy, expansion will continue forever, accelerating as time passes. In the distant future, galaxies beyond our local group will drift out of view, leaving only a small island of matter visible. The large-scale structure of the cosmos will fade into emptiness. A consequence of dark energy's dominance, dark energy is measured not just through supernova, but also through the cosmic microwave background. Galaxy surveys can baryon acoustic oscillations faint patterns in the distribution of matter left by sound waves in the early universe. These independent lines of evidence converge on the same conclusion. Dark energy exists and is the largest component of the cosmos. One gentle metaphor may place this in perspective. Dark matter is like the hidden scaffolding of a building, unseen but supporting its form. Dark energy is like a slow outward breath, expanding the space in which the structure stands. Neither is visible, but both define the shape and evolution of the universe. The coexistence of dark matter and dark energy highlights the incompleteness of current physics. The standard model of particle physics describes ordinary matter with great accuracy, yet it does not include dark matter or dark energy. General relativity explains gravity, yet we must extend it to include a cosmological constant or new fields. These gaps point toward new physics, perhaps unifying quantum mechanics and gravity, or introducing entirely new forms of matter and energy. Despite the mystery, we can describe their roles clearly. Dark matter pulls, gathering matter into galaxies and clusters. Dark energy pushes, driving space itself to accelerate outward. Together, they shape the cosmos on every scale, from the rotation of galaxies to the expansion of the entire universe. In summary, dark matter and dark energy are the unseen foundations of cosmology. Dark matter provides the invisible framework on which galaxies form. Dark energy drives the accelerating expansion that determines the universe's fate. Though unknown in composition, their effects are measured with precision. Just as a calm rhythm defines a moment even without being seen, dark matter and dark energy define the cosmos even without being directly observed. From this point, we can turn to the tools we use to uncover these mysteries: telescopes, detectors, and observatories that extend our senses, allowing us to map the unseen universe with ever greater clarity. The universe is vast, silent, and distant. To study it, humanity depends on tools that extend our senses far beyond what the eye can see. The story of cosmology is not only about theories and ideas, but also about instruments, telescopes, detectors, and observatories that make the invisible visible. These tools allow us to measure faint light, detect hidden matter, and probe signals from billions of years ago. Without them, our knowledge of cosmic horizons would remain only speculation. The most familiar tools are optical telescopes, which collect visible light from stars and galaxies. From Galileo's small lenses in the 17th century to today's giant mirrors, each generation has improved our ability to see deeper into space. Modern observatories, like the Keck telescopes in Hawaii or the Very Large Telescope in Chile, have mirrors more than 8 meters across, gathering enormous amounts of light. Adaptive optic systems correct for the blurring effect of Earth's atmosphere, giving nearly space-quality images from the ground. Yet visible light is only a small part of the electromagnetic spectrum. To understand the universe fully, astronomers need to observe across many wavelengths. Radio telescopes detect long wavelengths emitted by cold gas clouds and pulsars. Arrays such as the Very Large Array in New Mexico or the Square Kilometre Array under construction in South Africa and Australia combine signals from many dishes, acting as one giant instrument. Radio astronomy revealed quasars, pulsars, and the faint glow of the cosmic microwave background. Infrared telescopes look at cooler objects invisible to the eye, such as dust clouds where stars are born, or the faint light of distant galaxies stretched by redshift. Because Earth's atmosphere blocks much of the infrared, many instruments operate in space. The James Webb Space Telescope, launched in 2021, has already shown galaxies formed just a few hundred million years after the Big Bang. Its mirrors and detectors are cooled to near absolute zero. allowing it to capture faint signals that would otherwise be lost at shorter wavelengths. Ultraviolet, X-ray, and gamma-ray telescopes reveal the hottest and most energetic processes. Satellites like Chandra, XM Newton, and Fermi observe exploding stars, accreting black holes and cosmic rays. These high-energy instruments require space-based platforms, since Earth's atmosphere blocks such radiation. Each window adds a new perspective. Completing the cosmic picture. The electromagnetic spectrum, however, is not the only source of information. In recent years, astronomers have entered the era of multi-messenger astronomy. Gravitational wave detectors, such as LIGO and Virgo, measure tiny ripples in spacetime caused by colliding black holes or neutron stars. The first detection in 2015 opened an entirely new way of observing the universe. Neutrino detectors, buried deep underground or in Antarctic ice, capture fleeting particles that pass through ordinary matter almost without interaction. Together, these new messengers complement light, offering insights into regions otherwise hidden. Mapping the large-scale structure of the universe requires vast surveys. Instruments like the Sloan Digital Sky Survey use dedicated telescopes to record millions of galaxies, creating three-dimensional maps of cosmic filaments and voids. The Dark Energy Survey, using a 570-megapixel camera in Chile, traced hundreds of millions of galaxies to study dark energy. The upcoming Vera C. Rubin Observatory will scan the entire southern sky repeatedly, producing a dynamic map of the cosmos with unprecedented detail. Space missions also play a central role. The COBE, WMAP, and Planck satellites map the cosmic microwave background with increasing precision, showing the tiny fluctuations that seeded galaxies. Future missions aim to measure polarization in even greater detail, searching for signs of cosmic inflation. Observing from space removes atmospheric interference and allows continuous coverage across the sky. Each tool faces challenges. Telescopes must cope with faint signals, atmospheric distortions, and technological limits. Detectors require extreme sensitivity to register rare events like neutrino interactions or gravitational waves. International cooperation is often necessary, as the scale and cost exceed what any single nation can manage. Yet despite these difficulties, the progress has been steady, each generation of instruments revealing deeper layers of the cosmos. That one gentle metaphor may capture this work. Scientific tools are like carefully tuned ears, listening to different tones in a vast symphony. Some hear the low hum of radio waves, others the bright notes of visible light, others the sharp peaks of X-rays. Alone, each gives a fragment of the music. Together, they reveal the full harmony of the universe. The pace of discovery is accelerating. As computing power grows, telescopes and detectors generate enormous amounts of data, requiring new methods of analysis. Artificial intelligence helps identify patterns among billions of observations. International collaborations, like the Event Horizon Telescope, combine instruments around the globe to form planet-sized observatories. This effort produced the first image of a black hole's shadow in 2019, a milestone that shows how far tools can extend human vision. Looking ahead, the next generation of instruments will push horizons even further. The Nancy Grace Rumong Space Telescope will study dark energy with wide-field imaging. The Square Kilometer Array will map hydrogen across cosmic time. Gravitational wave observatories in space, like LISA, will detect signals from merging black holes billions of light-years away. Each of these projects extends our reach, gradually transforming questions about the unseen universe into measurable science. In summary, the tools of observation are the bridge between theory and reality. They gather faint signals, extend our senses, and reveal the universe across every scale and wavelength. Without them, concepts like horizons, dark matter, or cosmic geometry would remain abstract. With them, we transform silence into knowledge. Just as a calm rhythm makes hidden order perceptible, our instruments make the hidden universe visible. From here, it is natural to reflect not only on what these tools measure, but on what their discoveries mean. Beyond the technical details lies a deeper layer, the philosophical implications of studying horizons, boundaries, and the possibility that parts of the universe will remain forever unseen. Science describes the universe with measurements, equations, and models. Yet when we reach the boundaries of observation, when we ask what lies beyond horizons of space and time, questions arise that blend science with philosophy. These are not distractions from cosmology, but natural companions. For centuries, thinkers have reflected on what the cosmos means, how far knowledge can extend, and what it means for humans to inhabit such a vast reality. One central philosophical issue is the nature of limits. The observable universe is bounded by horizons, but those horizons are not physical walls. They are boundaries of knowledge. Philosophers ask, does something we cannot observe belong to the universe in the same way as what we can? Scientists tend to answer yes, based on the continuity of physical law. But strictly speaking, we cannot confirm what lies beyond. This raises the question of how far inference can extend before it becomes speculation. Another issue is the fine-tuning problem. Physical constants, such as the strength of gravity, the charge of the electron, or the mass of the proton appear delicately balanced. If they were slightly different, stars might not form, chemistry might be impossible, and life as we know it would not exist. Some see this as evidence of design, others as coincidence. Within science, one explanation is the anthropic principle. In a vast universe, or multiverse, observers naturally find themselves where conditions allow life. Philosophically, this invites reflection on necessity and contingency, whether the universe had to be this way or could have been otherwise. There is also the question of infinity. If the universe is infinite, then every arrangement of matter, no matter how improbable, could occur somewhere. Infinity challenges our concepts of uniqueness. It suggests that galaxies, stars, and perhaps even histories like ours might repeat endlessly. Philosophers debate whether infinity can exist in reality or only in mathematics. Cosmology confronts this question directly, since many models imply an infinite universe. The boundary of time raises further questions. If time began with the Big Bang, what does it mean to speak of before? Is a beginning without a cause intelligible? Some philosophers and theologians see this as evidence of creation. Others argue that time itself is a framework that does not need a cause. If time is eternal, new puzzles emerge. Can an infinite past exist? And if so, how does it flow into the present? These questions show how cosmology intersects with metaphysics, the branch of philosophy that deals with the fundamental nature of reality. Another theme is the role of human knowledge. The universe is vast beyond comprehension, yet fragile beings on a small planet can map its structure and trace its history back almost to its beginning. Philosophers of science ask what this means for the nature of knowledge. Are we discovering reality as it is, or constructing models that approximate truth? Scientific realism argues that our theories reveal actual features of the universe. Instrumentalism holds that theories are tools, useful but not necessarily true. The limits of observation, especially when discussing horizons, make this debate especially vivid. Philosophy also addresses the meaning of horizons. Horizons remind us that some parts of the cosmos are inaccessible. Does this mean that ultimate knowledge is impossible? Or does it show that knowledge is always contextual, expanding as tools improve, but never complete? Some thinkers suggest that this humility is itself a form of wisdom. Accepting limits does not weaken science. It clarifies what can be known and what must remain open. One gentle metaphor may illustrate this. Knowledge is like a lantern in a wide night. The circle of light shows us much, but beyond it lies darkness. The lantern's glow grows brighter with each discovery, yet the darkness always remains. Horizons in cosmology reflect this same relationship. Expanding knowledge reveals more of the universe, while also reminding us that something will always lie beyond. Philosophers also engage with the question of existence itself. Why is there something rather than nothing? Science can trace the universe back to the Big Bang and propose models of inflation or quantum origins, but it may never explain why there is a universe at all. Some argue this question is beyond science. Others believe future theories might address it. In either case, it shows the natural intersection between physics and philosophy. Ethical and existential reflections arise too. Knowing that the universe will expand forever, or that galaxies will drift beyond view, affects how we think about meaning. For some, the vastness inspires awe. For others, insignificance. Philosophers point out that meaning is not given by scale. Human life remains valuable, not because of cosmic size, but because of experience, consciousness, and the search for understanding. In this sense, cosmology both humbles and enriches our perspective. Finally, there is the dialogue between science, philosophy, and culture. Ancient traditions imagined the cosmos as finite, with clear boundaries. Modern cosmology shows a universe without edges, governed by laws that appear universal. This transition from myth to measurement does not eliminate wonder. Instead, it deepens it, placing humanity within a reality both knowable and mysterious. In summary, philosophical perspectives remind us that cosmology is not only about data and equations, but also about meaning and limits. They ask whether the unobservable is real, how to understand infinity, what horizons imply for knowledge, and why the universe exists at all. Just as a calm rhythm frames silence with order, philosophy frames science with reflection. It ensures that the search for the cosmos remains not only technical, but also deeply human. From here, we can turn to what these cosmic horizons and mysteries mean for us personally, how they shape our sense of place, belonging, and security within a universe that is at once immense and continuous. Cosmology often begins with equations and measurements, but it inevitably circles back to a deeply human question. What does all this mean for us? Standing on a small planet around an ordinary star, we look into a universe that stretches tens of billions of light years and contains matter and energy we cannot see. The scale can be overwhelming and the mysteries unresolvable. Yet reflecting on them shapes our perspective, our culture, and our sense of place in ways that are both humbling and enriching. One aspect of meaning lies in perspective. For most of human history, people believed the cosmos was small, centered on Earth, and designed for human purposes. The scientific revolution displaced this view, showing that Earth is one planet among many, orbiting an average star in a galaxy of hundreds of billions. Today, we know even that galaxy is just one among billions more. This shift does not reduce our importance, but reframes it. We are participants in a far larger story, connected to processes that began nearly 14 billion years ago. Another aspect is connection. The elements in our bodies, carbon, oxygen, iron, were forged in stars that lived and died long before the sun was born. Supernovas scattered these elements into space, where they became part of clouds that formed new stars and planets. In this sense, every breath we take carries atoms created in the hearts of ancient stars. The universe is not distant, but woven into us. Scientific knowledge deepens this awareness, showing that the same laws that govern galaxies govern our cells. Meaning also comes from the contrast between scale and intimacy. The universe is vast, but within it, life emerged, developed consciousness, and began to reflect on its origins. That reflection itself is extraordinary. The ability of humans to map the cosmic microwave background, to detect gravitational waves, to trace the curvature of space, these achievements show that fragile beings on a small planet can understand processes spanning billions of light years. It is a reminder that knowledge is not diminished by our size, but magnified by our curiosity. Some find the scale disquieting. The idea that galaxies will drift beyond view, that stars will eventually fade, that the universe may continue without end, these can create a sense of insignificance. Yet many philosophers and scientists respond differently. Meaning is not granted by size. It is created by awareness, experience, and connection. A single moment of understanding, a single act of compassion, or a single discovery carries value regardless of cosmic immensity. In this way, the vastness of the universe does not erase significance, but offers a backdrop against which human life shines clearly. The knowledge of horizons also influences our sense of security. Horizons remind us that not everything is accessible. There will always be regions beyond reach, mysteries unsolved. Far from diminishing us, this can bring comfort. It means the universe is larger than our grasp, ensuring there will always be more to explore, more to learn. A horizon is not only a limit, but also an invitation. A quiet boundary urging us forward. Culturally, cosmology shapes art, literature, and philosophy. Images of galaxies and nebulae inspire creativity. Concepts such as the Big Bang, black holes, and the multiverse appear in stories and metaphors across cultures. These are not mere borrowings of science, but reflections of how deeply cosmic ideas resonate with human imagination. They help us situate ourselves, not only scientifically but symbolically, within the cosmos. Education also gains meaning from cosmology. Teaching about the age of the universe, the life cycles of stars, or the role of dark matter connects students to questions larger than themselves. It fosters curiosity and humility at once. For many, this combination of awe and clarity inspires careers in science, art, or philosophy. In this way, the universe serves as a teacher, reminding us that wonder is a powerful motivator for knowledge. Ethically, awareness of our place in the cosmos can foster a sense of responsibility. Recognizing Earth as a small, fragile planet in a vast universe highlights the importance of caring for it. Environmental awareness, global cooperation, and the drive to explore space all draw strength from the realization that this planet is our home in an immense and possibly indifferent cosmos. Caring for it is not only practical but meaningful. One gentle metaphor may summarize this. Reflecting on the universe is like standing in a wide open field under a calm night sky. The field is vast, the stars are distant, but the act of looking upward ties the immensity to the intimacy of one observer. In the same way, cosmic horizons tie the largest scales of existence to the smallest, our thoughts, questions, and choices. In summary, the meaning for ourselves does not come from occupying a central place in the cosmos, but from understanding that we are part in it. The elements of our bodies come from stars. Our knowledge connects us to billions of years of history. Our reflections create significance even within immensity. The universe's vastness humbles us, but it also enriches us, giving depth to our experience and clarity to our responsibility. From here, it is natural to close the journey by gathering these threads together, summarizing what horizons, expansion, geometry, and mystery teach us about the cosmos and about ourselves. That brings us to the concluding reflections of this exploration. After following the trail from the observable horizon to the possibilities of other universes, from the expansion of space to the mysteries of dark matter and dark energy, it is time to pause and gather the threads. Cosmology is not only the study of distant galaxies or the early universe. It is also a discipline that reveals the boundaries of what can be known, the methods by which knowledge grows, and the perspectives these discoveries give us. The first thread is observation. Everything we know about the universe comes from signals that reach us: light, neutrinos, gravitational waves. Telescopes and detectors extend our vision, allowing us to reconstruct events billions of years in the past. These instruments remind us that science is not abstract speculation, but careful engagement with evidence. The boundaries of the observable universe are not arbitrary, but defined by the time light has had to travel, and the physics of expansion. The second thread is geometry and structure. The universe is not random but patterned. Galaxies form filaments and clusters, woven into a cosmic web shaped by gravity and dark matter. Space itself is flat to the limits of our measurement, balanced on the critical density of matter and energy. These facts are not trivial. They show that order exists even at the grandest scales, and that mathematics and observation converge to reveal it. The third thread is mystery. Dark matter and dark energy, together 95% of the cosmos, remain unknown in nature. Their presence is measured, their effects are clear, but their essence is hidden. The beginning of time itself is another mystery. Was the Big Bang a true origin or a transition from something earlier? These questions lie at the edge of physics, where theory and philosophy meet. The humility to admit what we do not yet know is as important as the clarity of what we do. The fourth thread is continuity. Horizons are not ends, but limits of connection. Beyond them, the universe almost certainly continues. The cosmological principle, the evidence of uniformity, and the predictions of inflation all suggest that our observable patch is one part of a much larger whole. Whether that whole is infinite or finite, flat or curved, part of a multiverse or unique, it reminds us that existence is not confined to what we see. The fifth thread is meaning. Cosmology reshapes how we understand ourselves. We are not at the center of the universe, yet we are capable of understanding it. The atoms in our bodies come from ancient stars. The light in our telescopes comes from the dawn of time. And the knowledge we build connects us to processes that span billions of years. This awareness can inspire humility, responsibility, and wonder. Taken together, these threads form a picture that is at once vast and coherent. The universe is not a static backdrop, but a dynamic reality, expanding, evolving, structured, and mysterious. Our place within it is not central in location, but significant in awareness. The act of studying horizons and asking what lies beyond them is itself a remarkable expression of human curiosity. One gentle metaphor may summarize this. The universe is like a book written on pages we can only partly read. The chapters available to us are rich and detailed, yet beyond them lie others still closed. We may never read every page, but what we have reveals a story of continuity, order, and openness. The mystery does not diminish the story. It deepens it. Cosmology does not end with certainty. It ends with openness to future observations, to new theories, and to questions that may never be fully resolved. This openness is not failure, but strength. It ensures that the study of the universe remains alive, always expanding like the cosmos itself. In closing, we can say this: the edge of the universe is not a wall, but a horizon. It is the limit of what we can know now, not the limit of what exists. Beyond it, space likely stretches farther than imagination, shaped by the same laws, and perhaps by laws we have yet to discover. The search for understanding is endless, yet every step gives clarity and perspective. Just as a calm rhythm gives structure to a quiet moment, the rhythm of discovery gives structure to our place in the cosmos. And so the journey ends not with a final answer, but with an invitation to continue observing, questioning, and reflecting. For as long as humanity looks at the sky, the horizons of knowledge will continue to expand, carrying us deeper into the story of the universe. The universe is not static, and neither is our knowledge of it. As tools improve and theories evolve, cosmology continues to expand into new frontiers. What lies ahead are discoveries that could transform our understanding of space, time, and existence itself. This closing chapter is not a summary of what we already know, but a look toward what science may reveal in the decades to come. One future horizon lies in the study of the cosmic microwave background with even greater precision. Current maps from Planck have already given us remarkable detail, but upcoming missions aim to measure polarization with far higher sensitivity. Detecting subtle patterns could confirm the presence of gravitational waves from the earliest moments after the Big Bang, offering direct evidence of cosmic inflation. Such a discovery would link theory with observation in a way that reshapes the foundations of cosmology. Another horizon comes from gravitational wave astronomy. Since their first detection in 2015, gravitational waves have already revealed merging black holes and neutron stars. In the future, space-based observatories like LISA will detect waves from supermassive black holes billions of light years away, or perhaps even from processes in the early universe. Gravitational waves provide a completely new sense, one that listens to the fabric of space-time itself. Dark matter remains a puzzle that future experiments may finally solve. Underground detectors are becoming more sensitive each year. Particle colliders like the Large Hadron Collider and its possible successors may reveal new particles. Astronomical surveys mapping gravitational lensing may further constrain its distribution. Whether dark matter turns out to be WIMPs, axions, or something more exotic, its discovery would be a milestone comparable to that of the electron or the neutrino. Dark energy is an even greater challenge. Current observations show that it drives cosmic acceleration, but its nature is still unknown. Future projects like the Nancy Grace Romang Space Telescope and the Euclid mission will map galaxies and measure cosmic expansion with unprecedented accuracy. These data may distinguish between a true cosmological constant and a dynamic field. They may even show whether dark energy changes over time. Such results will directly shape predictions about the fate of the universe. The study of black holes will also deepen. The Event Horizon Telescope has already imaged the shadow of the supermassive black hole. Improved arrays will sharpen those images, perhaps capturing the dynamics of matter falling in. Detecting the signatures of quantum effects near horizons could link relativity and quantum mechanics, two pillars of physics still awaiting unification. Another frontier lies in the search for life beyond Earth. Though not always framed as cosmology, the discovery of life elsewhere would change how we see our place in the universe. Telescopes are now able to detect atmospheres of exoplanets, searching for biosignatures such as oxygen, methane, or combinations that suggest biological processes. If evidence of life is found, it would not answer questions about cosmic horizons directly, but it would profoundly influence our interpretation of what it means to be part of the universe. Quantum gravity remains a theoretical horizon. Whether through string theory, loop quantum gravity, or another framework, scientists seek to reconcile relativity and quantum mechanics. Observational clues may come from high-energy astrophysics, gravitational waves, or signatures imprinted in the early universe. A successful theory of quantum gravity would reveal what happened at the very beginning of time and whether the Big Bang was a true origin or a transition. These scientific horizons are complemented by technological ones. Advances in computing, artificial intelligence, and international cooperation are transforming the scale of research. Projects involving thousands of scientists across continents are now standard. Instruments combine data from around the globe, effectively turning Earth itself into a single observatory. This collaborative nature reflects not only the scale of the universe, but also the shared human effort to understand it. One gentle metaphor may capture this outlook. Science is like a long journey across a wide ocean. Each island discovered is not the end, but a starting point for further travel. The horizon always shifts, always recedes, but it guides us forward. The search for cosmic truth is not a task with a final destination, but an ongoing voyage. Philosophically, the future of cosmology raises questions about the limits of knowledge. Will there always be horizons we cannot cross? Or will new tools gradually dissolve boundaries once thought permanent? History shows that horizons are not absolute. The CMB, once invisible, is now mapped. Gravitational waves, once hypothetical, are now detected. Each breakthrough extends the circle of light. It suggests that while mystery will always remain, knowledge will always grow. For humanity, these horizons offer both perspective and responsibility. They remind us that our place in the cosmos is small yet significant. Our ability to explore, to learn, and to reflect is itself a remarkable part of the universe's story. Each discovery links us more deeply to the cosmos, not as distant spectators, but as active participants in uncovering its nature. In closing, the future horizons of cosmology are not only scientific, but also human. They reflect our curiosity, our persistence, and our shared drive to understand existence. The universe will continue to expand, and so will knowledge. Just as a calm rhythm sustains continuity in a quiet moment, the rhythm of discovery will continue to guide us steady, unhurried, and open to what lies beyond. Thank you for sharing this quiet time with us. If you found peace or wonder here, feel welcome to like, comment, and subscribe. Your presence keeps this calm science flowing for all who seek rest and curiosity. Until our next gentle journey together, this was the Sleepy Brain Dose.